What if the first habitable alien world isn't light years away but already discovered? K2-18b, a distant exoplanet orbiting a cool red dwarf, has sparked global interest after signs of water vapor and potential biosignatures were detected. Could this be our second Earth? K2-18b resides 120 light-years away around a cool red dwarf, receiving just enough warmth to keep water liquid. Its 8 Earth masses and dense rocky ice composition suggest a deep ocean beneath high clouds. Spectral data hint at methane, raising hopes for microbial life in hidden seas. Early Hubble observations detected water vapor in K2-18b's atmosphere, the first such find on a super-Earth. Combined with James Webb Space Telescope infrared spectra, scientists now seek signs of clouds and potential rain, raising tantalizing questions about a water cycle in alien skies. K2-18b's host, a red dwarf named K2-18, emits most energy in infrared. Its low brightness means tidal locking likely binds one face in eternal daylight and the other in perpetual night. Models predict wind patterns driving heat from dayside to nightside, shaping unique weather systems. Methane detected in K2-18b's atmosphere could stem from geological processes or microbial life. Future missions aim to distinguish abiotic from biotic sources, looking for biomarkers like methyl chloride or ammonia. Such findings would transform our understanding of life's cosmic prevalence. If K2-18b has a rocky core, high gravity could crush its surface rocks into dense minerals. Beneath an icy crust, tidal forces may create pockets of liquid water under hundreds of kilometers of rock, forming subsurface seas warmed by internal heat. Wind speeds on K2-18b could exceed several hundred kilometers per hour, driven by extreme temperature contrasts. These winds might sculpt towering ice cliffs or carve deep gorges in the frozen crust, creating dramatic landscapes unlike anything on Earth. Some models predict K2-18b's surface pressure could exceed 100 atmospheres, creating a crushing environment. In such conditions, exotic ices, like superionic water, may exist, forming strange crystalline structures that conduct electricity deep below. Experiments in Earth labs recreate K2-18b's conditions, finding that hydrogen-rich atmospheres can remain stable with liquid water beneath. If similar chemistry occurs there, floating oceanic rafts of organic compounds might drift on periodic currents far above hidden seas. Future telescopes like LUVOIR or HABEX could image K2-18b directly, revealing continents of ice and clouds. A spacecraft, if ever launched, would face extreme radiation and cold, but could sample its atmosphere and dark ocean, unlocking secrets of alien biology. Mapping K2-18b's magnetic field could reveal shield strength against stellar flares. If strong enough, it might protect an ocean from evaporation and radiation. Without it, life in any form would struggle under relentless cosmic storms. Daytime temperatures on K2-18b's sunlit side might reach 50 degrees under thick haze, while the dark side plummets below 100 degrees C. This huge gradient drives storms that can stretch thousands of kilometers, merging ice and vapor in violent convection. If K2-18b has continents or floating ice platforms, explorers might navigate by light beacons or magnetic anomalies. Submarine voyages under thick ice could reveal exotic organisms adapted to high pressure and low light, microbial mats fed by hydrothermal vents. Future telescopes may detect seasonal shifts on K2-18b as its orbit tilts slightly over centuries. These changes could affect cloud cover and ocean currents, revealing weather cycles. Understanding them helps determine whether life can adapt to long, harsh seasons. Speculative probes might use swarms of tiny drones to map K2-18b's magnetic channels and weather patterns. Each microcraft would relay high-resolution data back to orbiters, piecing together a dynamic climate model for a world unlike any we know. Laboratory simulations of K2-18b's atmosphere reveal complex photochemistry. Under UV light from its red dwarf, organic precursors might form amino acids in floating haze. These could rain out, seeding subsurface oceans with building blocks of life. K2-18b's deep interior heat might drive volcanic activity beneath its frozen crust. These underwater volcanoes could supply minerals to the ocean, fostering chemosynthetic ecosystems that thrive without sunlight, sustained by chemical energy. An alien sunset on K2-18b would bathe the horizon in deep crimson, with two tiny moons trailing behind. Observers might glimpse shimmering auroras driven by charged particles interacting with its magnetic field. Over millennia, stellar evolution will transform K2-18's red dwarf into a faint white dwarf, dimming its light. K2-18b's once warm ocean could freeze solid, turning the planet into an icy wasteland devoid of life. K2-18b reminds us how fragile habitability can be, an ocean world teetering between life and ice. Whether microbial or barren, this distant planet reshapes our search for life, urging us to look beyond familiar shores into the vast unknown.